Hello, my name is Cristina and in this video I will explain the modeling process with neural networks. Neural networks are the most crucial technique for machine learning and artificial intelligence. Mathematically, we can formulate the modeling process with neural networks from a variational point of view. Indeed, building a model consists of finding a function that causes some functional to assume an extreme value. The following figure depicts a class diagram for the concepts involved in the modeling process. As we can see, the modeling process involves these concepts: dataset, neural networks, training strategy, model selection, testing analysis, and model deployment. Next, we introduce these 6 concepts. Dataset. The dataset contains the information for creating our model. The information may include numerical measurements, text, images, etc. It is a data collection structure as a table in rows and columns. A dataset comprises a matrix and information about the columns or variables and rows or samples. Variables can be used as inputs, targets, or unused, and samples can be used for training, selection, testing, or unused. The following is an example of a dataset in the automotive sector. An automotive company wants to build a digital twin of an electric motor using artificial intelligence. Having robust estimators of rotor and stator temperature helps the automotive industry to improve the motor's efficiency by reducing power losses and, ultimately, heat buildup. The company uses the dataset to build the model. The dataset comprises various sensor data collected from a permanent magnet synchronous motor, PMSM, deployed on a test bench. The LEA department of the University of Paderborn collected the testbed measurements. This dataset consists of 107 samples. The following table illustrates the dataset. In this dataset, all the variables are numeric. The input variables are ambient temperature, coolant temperature, voltage D, voltage Q, voltage module, current D, current Q, and current module. And the target variables are motor speed, torque, stator yoke, stator tooth, and stator winding. The samples are divided into 60% training samples, 20% selection samples, and the remaining 20% in testing samples. Neural network. An artificial neural network, or simply a neural network, can be defined as a biologically inspired computational algorithm consisting of a network architecture composed of artificial neurons. This structure contains a set of parameters tuned to perform specific tasks. The neural network represents the model. Neural networks are organized in layers. Approximation models typically contain 2 perceptron layers. Classification models usually contain a perceptron layer and a probabilistic layer. Forecasting models usually contain a recurrent layer and a perceptron layer. Other models, such as image classification model, include multiple convolutional and pooling layers and a perceptron or probabilistic layer. Neural networks have universal approximation properties. This means that they can approximate any function in any dimension with a desired degree of accuracy. The following is an example of a neural network in the automotive sector. To create this model, the company chooses a neural network. The following figure shows the neural network model. The neural network consists of 5 layers. The first is a scaling layer with 8 neurons. The 2 following are perceptron layers with 3 and 5 neurons, respectively. And the last is a probabilistic layer with 5 neurons. As we can see, the inputs to this neural network are ambient temperature, coolant temperature, voltage D, voltage Q, voltage module, current D, current Q, and current module. The outputs from the neural network are motor speed, torque, stator yoke, stator tooth, and stator winding. Training strategy. The objective of the training strategy is to feed the dataset to the neural network. The training strategy comprises the loss index and the optimization algorithm. The loss index defines the tasks the neural network is required to do and provides a measure of the representation quality that the model needs to learn. The choice of a suitable error term depends on the particular application. We can state the learning problem to minimize the loss index. The loss index for a neural network is composed of terms. The more important are the error term and the regularization term. The error term measures the difference between the outputs of the neural network and the correct predictions. We can use several types of errors. The most common error functions are mean square error, normalized square error, Minkowski error, cross-entropy error in classification problems, or square weight in binary classification problems. The regularization term can be applied to obtain a good generalization. Adding a regularization term to the error term will decrease the values of the biases and the neural network's weights. In consequence, the outputs of the neural network will become smoother, avoiding overfitting. One of the most used regularization methods is the norm of the neural network parameters. The primary purpose of the loss index is to avoid overfitting and improve regularization. The most commonly used optimization algorithms are gradient descent, conjugate gradient, quasi-Newton method, Liebenberg-Marquardt, stochastic gradient descents, and adaptive moment estimation. The following is an example of training strategy in the automotive sector. The automotive company creates a model to improve the efficiency of its engines. The loss index chosen is the normalized square error with L2 regularization. This loss index is the default in approximation applications. The optimization algorithm chosen is the quasi-Newton method. Once the strategy has been set, we can train the neural network. The following figure shows how the training, blue, and selection, orange errors decreased with the training epoch during the training process. The chart shows the both errors decrease until reaching a stationary value, so the algorithm converges. The most critical training result is the final selection error. It is a measure of the generalization ability of the neural network. The final selection error and training selection error are 0.083 and 0.029 respectively. Model selection. As we said before, building a model's objective is not to memorize the training subset but to show a good generalization capacity. The optimal architecture is the one that shows the best generalization capacity. That is the one for which the selection error is the lowest. We can analyze which input variables are redundant and delete from the input neural network, called input selection. It can be studied for which number of neurons the neural network shows the best performance, called neuron selection. When designing the neural network architecture, two common problems can occur: underfitting and overfitting. Underfitting is the effect that appears when the model is too simple. In this case, the neural network can be neither the training data nor the selection data. Overfitting is the opposite effect. It occurs when the neural network is too complex. Consequently, during the training process, the error for the training samples will decrease while the error for the selection samples increases. In both situations, the result is a model of bad quality. The following is an example of a model selection in the automotive sector. To achieve the model's optimal architecture, the company studies which input variables are redundant and with which number of neurons the neural network shows the best performance. This reduces the selection error in each model. They use the growing neuron algorithm to achieve the optimal number of neurons. The following figure shows the final neural network model. Therefore, the number of neurons in the perceptron layer has increased from 3 to 9, and the selection error has changed from 0.083 to 0.043. Testing analysis. Once the optimization algorithm has trained the model, we must evaluate its predictive ability on new data previously seen in the neural network. We use the test subset, which contains a set of new cases with their corresponding inputs and target variables. The goal of testing is to compare the responses of the trained neural network with the correct prediction for each sample in the test subset. We can use the result of this process as a simulation of what could happen in a real-world situation. One of the simplest methods to study the neural network's performance is calculating the error for the testing subset. If the model has not overfitting the training or selection instance, the training, selection, and testing errors should be similar. The most common method for testing regression models is the goodness of fit analysis. In the case of classification, the confusion matrix, the binary classification test, or the ROC curve are the quite common testing methods. There are also specific methods for testing forecasting models. Some of them are error autocorrelations and input error cross-correlations. If we consider the neural network good quality, we can move it to the deployment phase. The following is an example of a testing analysis in the automotive sector. The automotive company needs to test the model to check how well it fits a set of observations. To do this, they calculate the goodness of fit of a statistical model and the coefficient of determination R2. The total number of test samples is 21. The model's goodness on fit measures summarize the discrepancy between observed and expected values. The R2 coefficient quantifies the proportion of variation of the predicted variable concerning the actual values. If we had a perfect fit result equal to the objectives, R2 will be equal to 1. The following figure illustrates the predicted values versus the actual ones for the output stator yoke. The chart shows that the predicted values resemble the actual values. To give a quality measure, we calculate the coefficient of determination R2. Indeed, the regularization coefficient R2 is close to 1. Model deployment. The concept of deployment in machine learning refers to applying a model to predict new data. The deployment of a model consists of making it available to end users. There are many ways to deploy a machine learning model. The form of deployment depends on the requirements. Sometimes the end user wants a report with the results. On other occasions, they might need a repeatable continuous learning process. The following is an example of a model deployment in the automotive sector. The mathematical function describes the operation of the motor from the input data. The mathematical expression represented by the neural network is written below. The mathematical function is the final result of the study. The company can use it to achieve its objectives, to improve the efficiency of its current jobs.